Hello, and welcome to another video lecture for Machine Design ME372. I hope you all had a great Thanksgiving break and are ready to finish out the semester strong. In this video, we are going to review the failure criteria for cases where we have fluctuating stresses or non-completely reversed loading. And then we will work several example problems. So to begin with, remember this plot represents the failure envelopes for cases where we have non-fluctuate or non-reversed loading. So we have a fluctuating load. On the vertical axis, we plot the alternating stress, and on the horizontal axis, we plot the mean or the mid-range stress. Then we have several different curves. If we're inside the curve here, when we plot our alternating and mean stress, then we're safe. If we're outside the curve, then we are not safe and the part will not last for 10 to the 6th cycles. So there's a couple important curves that we need to make sure we're aware of. The first one is the Soderberg curve. And it goes from the endurance limit down to the yield strength. And it makes sense that if we had a completely reversed load, our mean stress would be 0, and we would come to this point here and come straight up, and we would fail at the endurance limit. Then as we increase the mean stress, the Soderberg line says failure occurs at the yield strength. The modified Goodman is a straight line between the endurance limit and the SUT. And the ASME elliptic is a parabolic curve that goes from the SE to the SY. And the Gerber is a parabolic curve that goes from the SE out to the SUT. So here are the equations of these different failure theories. I will expect you to have these equations memorized and be able to use them. And you can see that they are all very similar curves. We have the alternating and mean stress components in the numerators in every equation. For the Soderberg, we divide the alternating stress by the endurance limit and the mean stress by the yield strength. The only difference with the modified Goodman is we use the ultimate strength instead of the yield strength. Then in the Gerber, we haul the safety factor n to the other side and square the mean component. In the ASME elliptic, we haul the safety factor to the other side and square both components and change the SUT back to SY. So let's look at an example problem of how we use these curves. In this example, it says we have a stationary torsion bar spring-loaded statically by the forces of F of 35 kilonewtons and a torque T, which varies from 0 to 8 kilonewton meters. The material is AISI 4130 steel, heat treated and tempered. The ends of the spring are ground up to the shoulders. The 2.5 meter body of the spring has a hot rolled surface finish. The geometric stress concentration factors at the shoulders are 168 for bending and 142 for torsion. And then it says determine a suitable diameter D to the nearest millimeter using a factor of safety of at least 1.8. So let's go through and make sure we understand all the information that is being given to us in this problem. It first says that the stationary torsion bar, so we know that this bar here is not rotating. It is a fixed bar with a load on it that sees a torsion and sees a torque. This is not a spinning rod. We see that the constant force of 35 kilonewtons is applied at these points of 0.1 from the end. Then we have an alternating torque that is applied, and the alternating torque goes from 0 to 8 kilonewton meters. So this is a non-completely reversed stress or load. Then we get into a bunch of information that will give us the ability to compute the endurance limit. It tells us the material, it's heat treated so we can get the SUT. The ends of the spring are ground up to the shoulders, so that gives us a Ka factor. The 2.5 meter body of the spring has a hot rolled surface finish, so that gives us a Ka for the other part of the shaft. Then it gives us the geometric stress concentration factors, and these are big KTs. So we have a big KT for bending of 1.68 and for torsion of 1.42. Then it says use a safety factor of at least 1.8. So this is the safety factor 1.8. It's not a stress concentration factor. So down here I've listed all the information that's given and sorted it so that we can use it now to solve the problem. The basic approach to solve this problem is going to be to use the Goodman equation and solve for the diameter. Now we know that sigma A is a function of diameter, sigma M is a function of diameter, the SUT is the lookup value, but SE is also a function of diameter. We have a KB factor, which is the size factor, and that is a function of the diameter. So what we need to do is determine all of these terms in terms of the diameter, and then we will be able to solve this Goodman equation for the diameter. So to look at this problem, we're going to draw a shear moment diagram for the system. We can see that our shear force here jumps up and then drops back down to 0, comes over, drops down, and then jumps back up. So our moment diagram would jump up to a max, remain constant, and then drop down. And we would have a torque that would jump up, come across, and drop down. We can also draw the load diagrams for the loading on the shaft. And I would encourage you to draw these load diagrams because they really help understand the problem. Here I'm showing that the torque is an alternating between a 0 and a maximum value. And I can see that the bending stress is a constant mean stress. There is no alternating component on the bending stress. So I'm now going to break the components up into the alternating and mean parts. So computing the alternating stress, I know there are no normal alternating stresses, so sigma A is equal to 0. But I have an alternating shear stress due to Tc over J, and I can compute that value. Now Kt was given, and we need to use Kf. However, we don't know a notch radius. So one option is to assume Q equals 1, let the notch radius value be such that K is equal, or Q is equal to 1, and therefore Kf equals Kt. And this would give the worst Kf and would be conservative. Then once D is obtained, the notch sensitivity could be checked, and if it gave a significantly different Kf, that should be used. So on the alternating stress, we're going to go ahead and use the Kt value for Kf. And I'm going to come down here and compute my alternating stress component, my sigma A prime, which is the square root of sigma x squared plus 3 tau xy squared. Now note that up here sigma A equals 0, but that does not mean sigma A prime equals 0 because we have this torsional shear stress that comes in here. So I can solve for the sigma A prime and get 50 over d cubed. Now I compute the mean stress, and the mean stress has a sigma mean due to the bending, MC over I, and I can compute that value. And then I come and I compute sigma m prime. Here's my stress concentration factor and my sigma m, 3, and we also have a mean torsional stress given here. So the von Mises stress for the mean component is my bending stress plus my torsional shear stress, and this gives me 5160 over d cubed. Note, don't apply KT to ductile materials under static load, but under dynamic load we need to apply KF to the mean loads. So again, these should be KF values and not KTs. We're taking a worst case by taking KT, and it was really our only option because we cannot get a Q value with the given information. Now I'm ready to look at the endurance limit and determine the K values for the endurance limit. I was given a surface finish, and so I can look up the values for the surface finish that were given and get Ka as 0.396. Now I have a non-rotating round bar. D effective is given as 0.37 times D. So I compute D effective and I can get a KB value. But the problem with this is I don't know this D effective. This is the value that I'm trying to determine. So typically what will happen here is you will have a KB that's raised to this negative 0.107, and we'll have that in our endurance limit, and then when we go to stick that into our Goodman equation, we're going to have a D cubed from here and a D cubed from our alternating stress, and then when we stick those into Goodman back here, we're now going to have a D raised to the minus 0.107. And so typically what we do is we simply assume a KB value, and then we use that value and to solve the problem for the diameter so that we don't have to solve a challenging equation for D. So we're trying to solve for D. If we take the KB term and substitute it into the Goodman, it would be difficult to solve for D because D would be raised to multiple powers. So we're going to assume a KB value, we'll solve for the endurance limit, and then we'll solve for the diameter of the shaft. And then once we have the D, we go back and check our assumed KB value. And if we're close, we'll keep that D. If not, we pick a better KB based on our solution and resolve for D. So a good value to pick for KB, which is pretty close in most general conditions, is KB of 0.85. So we're going to assume a KB of 0.85. We'll have a Kc for bending of 1 and a Kc of 0.59 for torsion. We won't apply this because we have multiple loadings, so we'll use the stress equation that accounts for that already. We'll assume no temperature. We'll assume a reliability of 50%, so my endurance limit modified becomes 174.7. So in summary, I have all of these values here. I can now take them, substitute them into my Goodman equation, and solve for the D. And solving for D, I get D is equal to 84.5 millimeters. Now I need to check to make sure that the KB I assumed was a reasonable KB. So based on this diameter, I can now compute a D effective, which is 31.3 millimeters. I can stick that into the KB expression and I compute 0.852. So is 0.85 close enough to the 0.852? And it certainly is. So we do meet that assumes solution criteria, and the D that we solve for is fine. Now we need to check to see if we have a bigger diameter needed for yield. And so I come down here and I take the maximum alternating stress, the peak value of the alternating stress. And then I take the bending stress and I compute a sigma m prime. And the D for that is 56.7, which is significantly smaller than the 84.5. So, based on fatigue and yielding, the critical design diameter is 84.5 millimeters. Hopefully this problem makes sense to you. It's a good problem. It brings to light lots. This next example introduces what we do when we solve a finite life problem using the Goodman equation. So if we have alternating and mean stress components, we'll see what we can do to solve that problem in this example. Here it says the shaft shown rotates at 1720 RPM and is to have a life of 3 minutes. So it doesn't live for very long. The steel used has the following properties, SUT, E, and you love to see this fully corrected endurance limit. So this has been modified to account for all of the surface finish, size factor, and so forth. The shaft is simply supported in anti-friction bearings and is loaded by the static forces F1 and F2. So we have 2,000 pounds pushing down here, and we have 3,000 pounds pushing down here. Now we have a shear moment diagram that's given as shown here as our shear, and then our bending moment diagram is given here. Now I've already computed the critical stresses, and the critical stress location is this location A. Note that you would need to determine this location by computing the stress here at point A, as well as here at this peak value. And since this moment here is greater than what the moment would be over here, we know that it would be either this point A or this peak value here. So I computed this value and determined that it is here at point A. Now this is a completely reversed stress type of problem, but we're still going to illustrate the concept of using the Goodman in this type of situation. And so what we do is we come to the Goodman equation, and since we're not really going to have an endurance limit because this part won't have an infinite life, we stick in the fatigue strength at 5160 cycles. And 5160 is 3 times 1720. So I need to get the fatigue strength at 5160 cycles. Then my mean stress is 0, so that cancels out, and I can determine whether I have a safe design or not by computing my safety factor N. So SF at 5160 cycles is given by A equals N to the B. I can solve for A and I can solve for B, and then I can compute the SF and get 56,867. Now I can come back and compute my safety factor, and I get my safety factor is 1.2, which means the design would just barely be safe in a fatigue scenario. And this shaft would live for the design life of 3 minutes when rotating at 1720 RPM. So the critical thing here is to use the Goodman equation and replace it with a limited life stress, replace the endurance limit with a limited life stress or fatigue strength at a given number of cycles. This next example gives a very good example of how to use the Goodman equation for a finite life type of problem. And a problem like this is what you will see on the final exam. We need to make sure we can do a problem like this because it's also a very common problem in machine design, and it's a problem that you will likely encounter when you do stress analysis. So here we have a steel bar that undergoes cyclic loading such that we have a max of 60 and a min of minus 20. So we can see that we're not completely reversed, which indicates we need to use the Goodman failure equation. For the material, we have SUT, SY, and a fully corrected SE of 40, and little f is 0.9. It says estimate the number of cycles to a fatigue failure using Goodman and Gerber. So to do this, we first of all need to simply compute the stresses, the alternating and the mean components, and then plug them into the Goodman equation and compute our safety factor. So from the given information up here, we can determine our alternating stress, which is the difference of the max and the min divided by 2. And then we can determine our mean stress by the sum of the max and the min divided by 2. Plugging these values into the Goodman equation, after solving for the safety factor, we can see that our safety factor turns out to be less than 0.8 or less than 1, which indicates that this part will not live for an infinite life. It will not have 10 to the 6th cycles, but it will fail before that. So we need to determine how long the part will live. And what we do is we come to the Goodman equation and we replace the SE here with what we call sigma rev. And sigma rev is the equivalent reversed loading stress. And we'll solve for that sigma rev, and then we will use that to go back to an SN diagram and compute the number of cycles. So again, this is a very important point. If you have a safety factor in your Goodman that turns out to be less than 1, then you need to determine the number of cycles that the part will live for, and we do that by coming and replacing the endurance limit SE with what we call sigma rev, which is the equivalent completely reversed stress, which then lets us use an SN diagram. Now in the 11th edition of the textbook, sigma rev here is called sigma AR. And so you will see sigma AR in your text, and it is the same as this sigma rev here. Here it says this indicates the safety factor less than 1 indicates a finite life. The SN diagram is only applicable for completely reversed stresses. So to estimate the finite life for a fluctuating stress problem, we will obtain an equivalent completely reversed stress that is expected to be as damaging as the fluctuating stress. A commonly used approach is to assume that since the modified Goodman line represents all stress situations with a constant life of 10 to the 6th cycles, other constant life lines can be generated by passing a line through SUT, 0, and a fluctuating stress point, sigma M, sigma A. The point where this line intersects the sigma A axis represents a completely reversed stress, since at this point sigma M equals 0. So this sigma A predicts the same life as the fluctuating stress. So hopefully this makes sense to you. The completely reversed stress can be obtained by replacing the endurance limit SE with sigma rev in equation 646, which is the Goodman equation in this version of the text. So we then solve for sigma rev. So we'd come up to this equation here, we'd replace SE with sigma rev and solve this expression for sigma rev, and we get this expression here. So we see that this equivalent completely reversed loading stress, sigma rev, is 53.3. Now I can go use the SN diagram to determine the number of cycles. So I'll come over and compute the A, and I can compute the B, and now I use the number of cycles is equal to sigma rev over A raised to the 1 over the B, and I can get that 3.4 10 to the 4th cycles for the number of cycles using the Goodman equation. If I use the Gerber equation, I simply replace the Goodman with the Gerber, solve for sigma rev, and get the number of cycles. So one important point to note here is here we're predicting 4.6 times 10 to the 5th cycles. With Gerber, here we're predicting 3.4 times 10 to the 4th. And you can see how big the difference is between these two estimates. Now, the Gerber is usually moderate and not necessarily a conservative answer. The modified Goodman gives us a conservative answer in most all cases, and in fact, it often gives too conservative of an estimate. So that's why we see a big difference here, and it's important that if you were to do this design, you may want to look at several versions of the safety factor equation or failure theories and get a feel for the difference in the number of cycles based on the different failure theories. So this is a great example because it shows us how to do finite life with a fluctuating stress component. You'll want to make sure that you understand this problem, and that we now want to introduce the idea of cumulative fatigue damage. In many cases, a machine component doesn't just see a single load. For example, many parts may be subjected to an alternating and mean stress for 100 cycles, and then a different alternating and mean stress for 1,000 cycles, and then another set of stresses for another number of cycles. And a part typically may not see just a single mean and alternating stress component. And what we need to do is figure out how to account for the number of cycles that have already been put on a particular part. And we'll do that using the ideas of cumulative fatigue analysis. One of the trickiest parts about this type of analysis is determining the actual load cycle that the part sees. So we go through an example of that here. This figure A, shown here, shows that we have a load that starts at 60, jumps up to 80, drops down to 40, then back up to 60. And if this were one of the load cycles applied and this was repeated, that would be the load cycle. We're going to assume we have a second load cycle that goes from a minus 40 down to a minus 60, then up to minus 20, and back down to minus 40. So we have these two independent load cycles. And when we draw these load cycles, we know that in the machine part, they're actually going to be connected. And the connection is shown by these dashed lines here. Now, it may be that this tension load is applied 100 times, followed by 100 applications of this compressive load. But it may also be that we have the tension load followed directly by the compressive load. And in that case, we need to be careful how we draw the load cycle. Because what happens if we don't draw it carefully is we miss what we call a hidden cycle. So to do this, typically what you want to do is come to the peak value in the load cycle. and start your curve with this peak value. So I'm going to come here to the 80 and then propagate the curve out till it repeats itself back here again at the 80. And when I do that, I can see this dashed line illustrates an underlying hidden fluctuation curve, which in this case is actually the critical curve. So if we had just considered these alternating stresses and these alternating stresses, we would have missed this hidden underlying fluctuation, which is the critical stress cycle. So be careful when drawing these stress cycles that you again go to the peak value and then draw everything to the right, and you will see that you get an underlying curve. Now what we want to do is we want to put this graph into table form representing the cycles that need to be considered. And we do that on the following slide. So here's the same load diagram repeated. Now in my first cycle, I'm going to list my maximum stress, which is 80. Then I'm going to drop down here to the minus 60 and back up to the 80. And that will be my first load cycle. And that's the hidden load cycle. My second load cycle will go from this maximum 60 down to this minimum 40 and be this load cycle right here. My third and final load cycle will be the load cycle that goes from the maximum of minus 20 down to the minus 40 and this load cycle here. So hopefully you can see how we take this tension stress load cycle that was given and the compressive load cycle, and if they are followed by each other, then we draw the dashed line here and get what we call the hidden load cycle. And we draw our hidden load cycle as the dashed line, and then we have this cycle for cycle number 2 and this cycle here for cycle number 3. Now we can see that in this case, this first load cycle, which would possibly be missed, will be the critical load cycle because it's by far the largest stress range. When doing cumulative fatigue, there are several methods for counting the load cycles, and many of these methods are listed in your textbook in chapter 6. The method that we're using here and that we'll use in this text is a variation of what is called the rain flow counting technique. So let's now look at how we sum up and analyze the cumulative fatigue. And we do that using the Palmgren-Minor cycle ratio summation rule. And it's often referred to as just Minor's rule. And Minor's rule is written here as the summation of Ni over big Ni equal to C, where the little ni here is the number of cycles at the stress level sigma I. The big Ni is the number of cycles to failure at the stress level Ni. So this little ni represents the actual load conditions. The big Ni represents a strength type value. And big Ni would be the number of cycles at the strength or the maximum. And this is equal to C, and C is determined experimentally, and it's been shown to mainly fall between 0.7 and 2.2 with the average near 1. And we're going to introduce what we call the linear damage rule, and we're going to introduce this constant D, which is called the accumulated damage. And when D equals 1, failure occurs. So let's look at an example of how we do this. So given a steel part with SUT of 151 and the critical location of the part, SE 67.5, For this load case that we have analyzed, estimate the number of repetitions of the stress time block in figure 640 that can be made before failure, and we're to use the Morrow criteria. And if you recall, the Morrow criteria is very much like the Goodman, except we have replaced the SUT with sigma F prime, where sigma F prime is the SUT plus 50 in kpsi, or it's the SUT plus 345 MPAS. So we'll use the Morrow criteria to do this analysis and predict failure. So we come and we compute A and B and the number of cycles. And we have this given information, so we know the SUT. We can get F from equation 613 or from the plot and compute A, and we can compute B, and then we can come down here and get N once we have sigma rev or sigma AR. So we prepared to add the two columns in the previous table, and lacking material information, we're going to just estimate still and get sigma F prime to be 151 plus 50 to give me 201 kpsi. So now for cycle 1, I'm going to check the fatigue factor of safety to see if damage is expected. So using the Morrow equation, I can get my safety factor, and it turns out to be 0.92, so fatigue damage is expected. So from the completely reversed stress equation, equation 660, I get this expression, and I can solve for sigma AR as 73.7 kpsi, and I can come and solve for the number of cycles, which gives me 351 10 to the third cycles. Now I need to repeat this process with the second cycle of stress. So I'll come down here and use my Goodman equation, and I see here that my safety factor is greater than 1. It's 2.52, so no fatigue damage will be expected from cycle 2. So from my first cycle here, cycle number 1, we can see that fatigue damage was expected. Now from cycle number 2, which is a very small cycle, we determined that the safety factor is greater than 1 and there will be no fatigue damage. So the number of cycles here would be an infinite number of cycles, or 10 to the 6th. Then in cycle number 3, we see that this cycle has negative mean stresses, and so we won't have crack propagation here, and we can also have an unlimited number of cycles. So I now come down to compute big D, and big D then would be Ni over Ni equals, pull out the N from this expression, 1 over the 351 plus 1 over infinity plus 1 over infinity for the second and third load cycles. And so I have this expression here. Now I set big D equal to 1, and I solve for N, which yields 351 times 10 to the third cycles. So my part, given this load cycle shown here, would be able to see or experience 351 10 to the third cycles. So hopefully this shows you how we use the Miner's rule and the cumulative fatigue damage idea to estimate the number of cycles.